So let's talk about acid-base effects. And one of the points of confusion people are having is about induction and kind of what are some examples of induction and what's really going on here, right? So induction is just another way of talking about electronegativity, but not when the atom we're talking about is not directly attached to the hydrogen, right? So it's different than something, or say if we compare HF and HI, right? When that's really all about size and orbital overlap, things that are similar in size will be able to share their electrons more efficiently, percentage-wise, versus like a big old atom and a little atom, right? So think about a giant elephant with a little bug, a little gnat on its bottom, right? That's like a hydrogen and an iodine, right? So this makes this more reactive. But this is not induction. This is not induction. So what is something like induction? So one of the examples I think we looked at was something like this versus that. And so people got confused, and this happens a lot. People want to say, well, wait a second, bromine and chlorine. Okay, they're in the same column. Oh, size, right? Size. That's the answer, size. Must be about size. It's not about size, right? It's not about size. It's really about, induction is really about electronegativity, right? Who's going to pull electrons more, right? And polarize, right? We're talking about the OH bond in each, right? And they both the OH products would have resonance, so that's all the same. So the only thing that's different is this chlorine and bromine. So you're right, bromine is bigger than chlorine. But that's not what matters here. Which one's more electronegative? Which one's smaller? Chlorine or bromine? Put it in the chat. Chlorine or bromine? Put it in the chat. Let's see. Who's smaller, chlorine or bromine? Chlorine or bromine? Very good. Chlorine is smaller. So if you're smaller, what that means is, right, your outer shell of electrons is closer to your nucleus. You're more electronegative, right? So smaller atoms are going to be a little more electronegative. So in this case, the chlorine is going to pull or polarize, right? Think about pulling more than a bromine would. So that's going to make this more acidic because of induction, this part here. How else can we use induction? There's lots of fun ways. Distance matters. All right, so if I have A and B, right, what's the same, what's different? So it's still an OH bond. Whoops. It's still an OH bond, right, in both. It's still a fluorine in both. So what's different? In B, the fluorine's farther away from the OH, right? The fluorine's farther away from the OH. So which one's going to have a bigger effect? The fluorine that's closer or the fluorine that's farther away? Say it. Say it out loud. Let's hear your voices. Closer or farther away? Which one's going to matter? Close, far. Close.
Closer.
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 I have a quick question.
Yes.
Is there a certain distance?
So what other ways can we do induction? So there's always this classic way, same atom, farther away. Easy, that makes sense. And we just did different atoms, same distance away. Which one's more electronegative? Makes sense. Another fun thing to do would be, what if we had two versus one? Which one's going to be more acidic? Which one's going to be more acidic here? Which is going to have a more acidic OH bond? A or B? The one with two fluorines, the one with one fluorine.
A.
A, right? Now somebody should ask, oh, wait a second. What if you put one fluorine, but then put two chlorines 3 bonds away and one fluorine 1 bond away? I'm not going to do that, right? I'm not going to do that. That's too hard to. You got to isolate the question, right? So I'm not going to do I'm not going to do something where, right? I don't know. You know what I'm saying. That's a good wrap up. Essentially, the way induction can work: different atoms, different electronegativities, same distance. Which one's more electronegative rules the day. Same atom, different distances. The closer one has a bigger effect. Same atom, same distance, but more of one. That makes a bigger effect too. All right. So in this case, this is on 20.4.2. We have pyridine, Parole, and furan. You don't need to know the names, but those are the names. What we're looking at here is essentially these lone pairs in all of them. And what we're really kind of asking is, how reactive are those? So this is an acid-base kind of reaction about hybridization state and hybrid orbitals. And when we ask about how reactive a lone pair is, we're really asking how basic is it? How nucleophilic is it? How willing is that lone pair willing to react? So things you need to ask yourselves, right? So I'm asking about reactivity of this lone pair. Is it in resonance?
I don't know if it's.
So we ask ourselves, is the lone pair in resonance? We ask ourselves, is the lone pair or what hybrid orbital does the lone pair reside in? Right? Because what hybrid orbital will tell us something about how reactive it is, right? If a lone pair is in a sp3 orbital, that's farther from the nucleus. That's more reactive than an sp orbital that has a lone pair, right? We learned about that with hybridization. And we really need to start thinking about these molecules in 3D, right? In 3D structures. So let's take a look at that. I'll try to redraw that for you. Okay, so there's pyridine in 3D. See how I made the p orbital system, right? All of these atoms are sp2 hybridized, right? They all have one pi bond, so they're sp2 hybridized. But the question we're asking about here is, what about this lone pair? What hybrid orbital is that lone pair in? If this nitrogen is sp2 hybridized, this lone pair is where? It's over here in an sp2 hybrid orbital. Is that lone pair able to do resonance with this? Is it able to do resonance with this? No.
No.
No, it has to be lined up, right? Do resonance, you have to be lined up in that p orbital system. It's not lined up, right? It's not lined up. What about Parole? So what's that? Okay, well, one step. What's that going to tell you about this? So if it can't do resonance, is that going to make it more reactive or less reactive in this case? If you're doing resonance, you're sharing your electrons around. If you're sharing electrons, are those electrons able to react? No. Can this lone pair, nitrogen, share its electrons? Is it delocalized? No, it's localized. So it's going to make this a pretty good base, a pretty good nucleophile. It's going to make it pretty reactive. That lone pair is a little more reactive. What about Parole? All right. So now I just drew Parole. This nitrogen has what kind of bonds? It has 3 sigma bonds. So normally we'd think it'd be sp3 hybridized, right? But since this lone pair is next to a pi bond, it's going to be sp2. And it's going to put that lone pair where? It's going to put it into a p orbital. There's those 2 electrons. It's in a p orbital. This lone pair is now part of the p orbital system. Is this lone pair going to be very reactive? If it's part of resonance? No. Right? No, it won't be. So what I want you to think about is furan. Now this oxygen has 2 lone pairs. What's that structure going to look like? One lone pair is going to be where? In what kind of hybrid orbital? A p orbital. So one lone pair is going to be in a p orbital. The other lone pair is going to be in an sp2 orbital. Now, some people are like, well, which one's which? I mean, it doesn't matter. Like, sometimes people will draw it inside the ring, and then that's supposed to be the p one. Don't worry about that. Just pick one. One's in the p, one's in the sp2. It doesn't matter. Okay. What about this? So this is acetonitrile. Acetonitrile. What's the hybridization state of this nitrogen? It is sp hybridized. Good. Where is this lone pair at? What hybrid orbital is this lone pair in?
SP.
sp. Very good. Would you guess what's more reactive, acetonitrile lone pair or the pyridine lone pair? Which one's going to be more basic? Which one's more reactive? Which one's farther from the nucleus?
Would it be the peer?
The pyridine, yeah. Right? This is going to be more reactive because this hybrid orbital is farther from the nucleus, so it's more reactive versus an sp hybrid orbital with a lone pair.